Hello my dear students, in this lecture we are going to learn dual cycle. This dual cycle is also called Sabate cycle. It is also called as Sabate cycle. Now here, before understanding this dual cycle, let us recall the things from Otto and diesel cycle, right? Because already we have learned Otto and diesel cycle. Now here we are going to see the comparison between Otto, diesel and dual cycle on the basis of few parameters. Now here the parameters are fuel used, compression ratio, heat addition, heat rejection, suction and temperature at the end of compression process. These are very important parameters for comparison of any cycles, right? For Otto cycle, the fuel used is petrol. Therefore, it is also called petrol engine. Otto cycle is also called petrol engine. Now, here for diesel cycle, the fuel used is diesel. Therefore, it is also called diesel engine. And my dear students, for dual cycle also, the fuel used is diesel. It is diesel. Hence, as for diesel cycle and for dual cycle, the fuel used is diesel. Hence, this dual cycle is also called semi-diesel cycle. Therefore, this dual cycle is also called semi-diesel cycle. Now, the next parameter for the comparison is compression ratio. Compression ratio is represented by RK and it is nothing but ratio of volume at the entry of compression V1 to the volume at the exit of compression V2. Now, for petrol engine, that is for Otto cycle, this compression ratio RK is nothing but 6 to 12. The range is 6 to 12. For diesel cycle, this compression ratio is nothing but 16 to 22. 16 to 22. And my dear students, for any comparison, the dual cycle is always in between Otto and diesel cycle. That's why while writing here, I have written this dual cycle in between Otto and diesel. Right? For any comparison, dual cycle is always in between Otto and diesel cycle. So here the compression ratio for dual cycle is 12 to 16 in between Otto and diesel. Now heat addition. Now heat addition is nothing but heat supply. During this process, heat is supplied or heat is added. Now for Otto cycle, the heat addition is at constant volume process. Therefore, heat addition process is constant volume for Otto cycle. For diesel cycle, the heat addition is at constant pressure process. For diesel cycle, heat addition is constant pressure process, we can say, right? Now, for dual cycle, the heat is added first at constant volume and then at constant pressure. Therefore, for diesel cycle, heat is added both at constant volume as well as constant pressure processes, right? This is the heat addition order. And first of all, firstly the heat will get added at constant volume and after that the heat will get added at constant pressure. Now next comparison is heat rejection. Heat rejection is also represented by QR. And my dear students, for Otto, diesel as well as dual cycle, heat is always rejected at constant volume process. Therefore, for all, heat is rejected at constant volume process only. Right. Now, whenever heat is at constant volume, it is represented by mCv, change in temperature. And whenever heat is at constant pressure, it is represented by mCp, change in temperature. Right. For constant pressure process, we have to use Cp, and for constant volume process, we have to use Cv. Now, next comparison is suction. My dear students, during suction stroke for Otto cycle, air plus fuel mixture is taken in, and for dual and diesel cycle, only air is taken in. Therefore, during suction for Otto cycle, air plus fuel mixture is taken in the cylinder, and for dual as well as diesel cycle during suction only air is taken in, only air for both is taken in. Now last parameter is temperature at the end of compression. The temperature at the end of compression is nothing but T2, and this temperature at the end of compression T2 is nothing but Rk raised to gamma minus 1 into temperature at the beginning of compression T1. T1 into Rk raised to gamma minus 1, and this temperature we have to compare, right? This T2 at the end of compression for Otto cycle, my dear students, this T2 is less than self ignition temperature. It is less than self ignition temperature. Therefore, as this temperature is less than self ignition temperature, in case of petrol cycle or Otto cycle, we need to use spark plug for the ignition. Therefore, this Otto cycle is also called spark ignition engine, SI engine, spark ignition engine or SI cycle, SI engine cycle, right? Now, for dual as well as diesel, this temperature at the end of compression T2 is more than self ignition temperature of the fuel, right? For both diesel as well as dual, this T2 is more than self ignition temperature of the fuel. Hence, as this temperature is more than self ignition temperature, we need not to use spark plug. Therefore, these dual as well as diesel cycle are called compression ignition engines. Hence, this diesel cycle is called compression ignition engine, that is CI engine. Now, let us understand this dual cycle on pressure versus volume and temperature versus entropy diagram. Let us say we have one engine. Engine is nothing but piston cylinder assembly. Let us say this is a cylinder of an engine. Now here, inside this cylinder, the piston is reciprocating from two dead centers. That is, one is top dead center. Let us say this is a top dead center TDC, and bottom dead center. There is a bottom dead center BDC. BDC. Now between these two dead centers, piston is reciprocating. Right. Now here, let us draw PV and TS diagram for these two dead centers. Let us say there is a pressure versus volume diagram. Pressure versus volume diagram. This is a PV diagram. On y-axis there is a pressure, on x-axis there is a volume, and there is a temperature versus entropy diagram. On y-axis there is a temperature, on x-axis there is a entropy. Now let us say the initial position of piston is at top dead center. Now let us say this position is represented by 0, top dead center 0. Let us mark these top dead center and bottom dead centers on PV diagram. Here this line will be the top dead center, and here another line for bottom dead center. Means piston can reciprocate between these two lines only, right? Now whenever the piston is at TDC, that is 0 position, the condition inside cylinder is atmospheric condition. Therefore pressure at 0, this at 0 location, pressure is atmospheric pressure, P atmospheric, right? And when piston starts moving from top dead center to bottom dead center, the inlet valve is opened. So just open the inlet valve. This inlet valve will be open, and now piston is moving from top dead center to bottom dead center. Hence there will be a suction stroke, and during this suction stroke only air is taken in. Only air is taken in during suction stroke for the dual cycle, right? Therefore piston will move from top dead center to bottom dead center during suction stroke, and to maintain the inside pressure equal to atmospheric pressure, the outside air will go into the piston cylinder assembly. Therefore from 0 to 1, let us say the piston is at BDC, that is one location. From 0 to 1 there is constant pressure suction process, right? Therefore 0 to 1 the pressure will remain constant, and during this process there will be a suction, right? We can say 0 to 1 is suction stroke, and during this stroke the pressure is constant. Therefore constant pressure suction stroke, that is pressure at 0 is equal to pressure at 1 is equal to atmospheric condition. Now once the piston reaches at bottom dead center, now close this inlet valve. Now the inside air is compressed from bottom dead center to top dead center reversibly adiabatically. Therefore from 1 to 2 again, that is BDC to TDC, at TDC this is a 2 location, from 1 to 2 there is a reversible adiabatic compression. Therefore 1 to 2 on PV diagram the process will be like this: 1 to 2 reversible adiabatic compression, 0 to 1 is constant pressure suction, 1 to 2 is reversible adiabatic, means PV raised to gamma is equal to constant, and compression, right? Now my dear students, whenever piston reaches at TDC, that is 2, the temperature at the end of compression T2 is more than self ignition temperature, of fuel. Hence as this temperature is more than self ignition temperature, this air, inside compressed air, is waiting for the fuel to get ignited. Therefore here we will use fuel injector. In case of this we will use fuel injector. This is a fuel injector. Now from this fuel injector the diesel is sprayed in the form of sprays, and as soon as diesel comes into the system as the temperature is more than self-ignition temperature, the ignition starts. And my dear students, for some portion of time, the heat is added at constant volume. Means whenever piston is at TDC only, heat gets some quantity of heat gets added. Therefore, it is heat supply at constant volume. This is a heat addition at constant volume. Therefore, from 2 to 3, there will be a heat supply at constant volume. 2 to 3 heat supply at constant volume. This is a constant volume process. Therefore, this point 2 and 3 will be at same location in piston cylinder assembly. Now, from 3 to 4, the heat gets added at constant pressure process. Therefore, the piston will go to the 4 location, and during this 3 to 4 the pressure remains constant, and it is heat supply at constant pressure process. Therefore, 3 to 4 like this 4, this is a constant pressure heat supply process. And once the piston goes to the 4, from 4 to 5, that is 4 to BDC, the piston moves reversibly adiabatically. Therefore, at 1 on piston cylinder assembly, there is 5 point also. Now, from 4 to BDC, it is reversible adiabatic expansion process. Therefore, 4 to 5, there will be a reversible adiabatic expansion. This is a, we can say this process is reversible adiabatic expansion. There will be a 5 point. Now here you can see that the pressure at the end of expansion, that is P5, is more than inlet pressure to the cycle P1. Therefore, as this P5 pressure at the end of expansion is more than pressure at the entry of compression P1, hence because of this pressure difference, the exhaust gases inside this piston cylinder assembly will move outside if exhaust valve is open. So here I will open the exhaust valve so that the 90% exhaust gases will move out whenever the piston is at BDC only. Because of this pressure difference, we can say 90% exhaust gases will move out of this piston cylinder whenever the piston is at BDC only, and the inside pressure becomes equal to P1, right? Therefore, we can say the heat rejection is at constant volume process. Now, to throw out remaining 10% of exhaust gases, we have to move this piston from BDC to TDC. This is called exhaust stroke. To move remaining exhaust gases, we have to move piston from BDC to TDC, that is 1 to 0 again, 1 to 0 again. This is called exhaust stroke, and during this exhaust stroke, the pressure remains constant. Now here, my dear students, if you observe the cycle carefully, 0 to 1 is suction stroke, 1 to 0 is exhaust stroke, and these suction and exhaust stroke are not the part of cycle, because cycle is from 1, 2, 3, 4, 5 only. This is a cycle, right? So my dear students, I will consider this cycle only, that is 1, 2, 3, 4, 5 only. Now the process 1 to 2 is reversible adiabatic compression. Reversible adiabatic compression means isentropic compression, and during this process temperature increases. Therefore, from 1 to 2, at constant entropy temperature increases. 1 to 2 constant entropy temperature increases. Now 2 to 3 is constant volume heat supply process. Now therefore, on TS diagram, the slope of constant volume process dt by ds for constant volume process is nothing but T by Cv on TS diagram, that is positive slope. Therefore, as heat is added, temperature increases and entropy also increases. Therefore, 2 to 3 is constant volume heat supply process. Constant volume heat supply process. Now, again 3 to 4 is constant pressure heat supply process, and we know that for constant pressure heat supply, the slope on TS diagram dt by ds at constant pressure is nothing but plus T by Cp. Again, slope is positive, and my dear students, Cp is always more than Cv, that already we have learned in basic thermodynamics subject. And these all concepts, this slope concept you have learned in basic thermodynamic concept, that is entropy topic, right? Now Cp is always more than Cv, therefore I can say T by Cv is more than T by Cp, because here denominator is more for T by Cp and denominator is less for T by Cv. That means the slope of constant volume process on temperature versus entropy diagram is more than slope of constant pressure process on temperature versus entropy diagram, right? Therefore, from 3 to 4, the pressure line will be like this 3 to 4 pressure is constant, but here you can feel that the slope of 2 to 3, that is constant volume process, is more than the slope of 3 to 4, that is constant pressure process, right? If I extend the slope of 2 to 3, you can feel here the slope of constant volume process is always more than slope of constant pressure process on TS diagram, temperature versus entropy diagram. Now 4 to 5 is reversible adiabatic expansion, that is PV raised to gamma is equal to constant. Therefore reversible adiabatic expansion means isentropic expansion, that is entropy remains constant and during this process temperature drops. Therefore 4 to 5 there will be at constant entropy temperature drops. Now 5 to 1 is constant volume heat rejection. Therefore again 5 to 1 there will be a constant volume heat rejection. At constant volume heat will get rejected from the system. Therefore this is a TS diagram. On TS diagram 1 to 2 reversible adiabatic, that is isentropic compression, 2 to 3 constant volume heat supply, 3 to 4 constant pressure heat supply, 4 to 5 reversible adiabatic, that is isentropic expansion, and 5 to 1 constant volume heat rejection. So here I am writing various processes on PV and TS diagram. The number one is 1 to 2. 1 to 2 is reversible adiabatic. It is reversible adiabatic compression, also called isentropic compression. And for this process, there will be a compression ratio, that is RK. Compression ratio is nothing but ratio of volume at the entry of compression, that is V1, to the volume at the exit of compression V2. Now next process is, that is 2 to 3 is heat addition at constant volume heat supply. And for this process there will be a explosion ratio, and this explosion ratio is represented by RP, and this is a pressure ratio, that is P3 divided by P2, and called explosion ratio. Now third process is 3 to 4, and 3 to 4 is constant pressure heat supply process. And for this constant pressure heat supply process, we have seen that there will be a cutoff ratio RC, and cutoff ratio is nothing but V4 divided by V3, volume at the end of heat addition divided by volume at the entry of heat supply. The process number 4 is reversible adiabatic expansion. That is process 4 to 5. Here you can see 4 to 5 is reversible adiabatic expansion. Therefore for this process there will be an expansion ratio RE, which is nothing but the volume at the end of expansion V5 divided by volume at the entry of expansion V4. This is called expansion ratio. And the last process number 5 is 5 to 1, which is nothing but a constant volume heat rejection. At constant volume heat rejection. These are the various 5 processes on PV and TS diagram. Now let us do the analysis of various processes on PV and TS diagram. Now very first process, that is 1 to 2, it is a reversible adiabatic compression. Therefore equation of this process is T2 divided by T1 is equal to P2 divided by P1 raised to gamma minus 1 upon gamma is equal to V1 divided by V2 raised to gamma minus 1. And this V1 divided by V2, that term we have called as compression ratio, which is nothing but RK raised to gamma minus 1. Therefore T2 divided by T1 is equal to RK raised to gamma minus 1. Therefore from this we can say this T2, temperature at the end of compression, is equal to T1 into RK raised to gamma minus 1. This is the first equation which is useful later. So this equation I am writing here. This T2 is equal to T1 RK raised to gamma minus 1. This equation is required later, right? Now second process, that is process number 2 to 3 is constant volume heat supply. Therefore at constant volume pressure is directly proportional to temperature. Therefore the pressure ratio can be replaced with temperature ratio. Therefore we can say T3 divided by T2 is equal to P3 divided by P2. And my dear students, this P3 divided by P2 is explosion ratio, that is RP, therefore is equal to RP. Therefore we can say T3 is equal to T2 into RP. And from equation number 1, T2 is T1 RK raised to gamma minus 1. So put here in T3. Therefore we will get this T3 is equal to T2 into RP, which is nothing but T2 is T1 RK raised to gamma minus 1 into RP. This is second equation, and this equation is also useful later. Therefore I am writing here T3 is equal to T1 RK raised to gamma minus 1 into RP. This is the T3. And as process 2 to 3 is constant volume heat supply, therefore heat supply at constant volume process is equal to mCv T3 minus T2. For constant volume processes, we have to use specific heat at constant volume Cv. So therefore heat supply at constant volume process is equal to mCv T3 minus T2. This is also useful later. Now third process is 3 to 4, that is heat supply at constant pressure. 3 to 4 is heat supply at constant pressure process. Therefore again for constant pressure process, volume is directly proportional to temperature, therefore volume ratio can be replaced with temperature ratio. So we can say T4 divided by T3 is equal to V4 divided by V3, and this V4 divided by V3 is nothing but cutoff ratio, therefore is equal to RC. From this we can say T4 is equal to T3 into RC, and this T3 from the equation number 2 is T1 RK raised to gamma minus 1 into RP. Put here, therefore is equal to T1 RK raised to gamma minus 1 into RP into RC, and this is equation number, let us say, 4, because heat supplied constant volume is third equation here, right? So this is also required, therefore T4 is equal to T1 into RK raised to gamma minus 1 into Rp into Rc. And my dear students, this process 3 to 4 is heat supply at constant pressure process, therefore heat supply at constant pressure is equal to mCp T4 minus T3. And for constant pressure process, we have to use specific heat at constant pressure, that is Cp. So this is your fifth equation. Again this is useful, therefore heat supply at constant pressure process is equal to mCp T4 minus T3, useful later. Now next process, that is 4 to 5, that is reversible adiabatic expansion. Fourth process is reversible adiabatic expansion. Therefore for this process, the temperature ratio T4 divided by T5 is equal to P4 divided by P5 raised to gamma minus 1 upon gamma is equal to V5 divided by V4 raised to gamma minus 1. And my dear students, this V5 divided by V4 is expansion ratio, which is nothing but Re raised to gamma minus 1. Therefore we can say this T4 divided by T5 is equal to Re raised to gamma minus 1. From this we can say T5 is equal to T4 divided by Re raised to gamma minus 1. And my dear students, use the T4 value here. T4 is T1 RK raised to gamma minus 1 into Rp into Rc. So the equation becomes T5 is equal to T1 into RK raised to gamma minus 1 into Rp into Rc divided by Re raised to gamma minus 1. And my dear students, we know that compression ratio Rk is equal to V1 divided by V2, expansion ratio Re is equal to V5 divided by V4, and cutoff ratio Rc is equal to V4 divided by V3. Now let us say here Re into Rc is equal to V5 divided by V4 into V4 divided by V3, which is nothing but V5 divided by V3. And my dear students, this Re into Rc is equal to V5 divided by V3, and this 5 to 1 is constant volume process, therefore V5 is equal to V1 is equal to V1 divided by 2 to 3 is constant volume process, therefore V3 is equal to V2 divided by V2, and V1 by V2 is Rk. Therefore the compression ratio Rk is a product of expansion ratio and cutoff ratio. From this cutoff ratio is equal to compression ratio divided by expansion ratio, right? So my dear students, in T5 equation, here you will find that in T5 equation there is Rk raised to gamma minus 1 divided by Re raised to gamma minus 1. Therefore this Rk divided by Re raised to gamma minus 1 can be written as Rc raised to gamma minus 1. So we will replace this Rk raised to gamma minus 1 divided by Re raised to gamma minus 1 with Rc raised to gamma minus 1. Therefore this T5 becomes equal to T5 is equal to T1 into Rc raised to gamma minus 1 into Rp into Rc. So my dear students, this Rc raised to gamma minus 1 into Rc, this will become Rc raised to gamma. Therefore T5 is equal to T1 into Rp into Rc raised to gamma. This is again our next equation, let us say equation number 6. Therefore it is T5 is equal to T1 into Rp into Rc raised to gamma. It is again useful later. Now the last process, that is process number 5, that is 5 to 1, is constant volume heat rejection. Therefore as it is constant volume heat rejection, heat is rejected at constant volume, which is nothing but mCv T5 minus T1. For constant volume process we are using Cv. Therefore heat rejected is equal to mCv T5 minus T1, right? Now let us find the efficiency of this dual cycle, because the efficiency is very important parameter. As we have calculated for auto and diesel cycle, let us find for dual cycle. Therefore, efficiency of any cycle, efficiency of dual cycle is equal to, we know that 1 minus heat rejected divided by heat supply. This is the formula to find efficiency of any cycle. Now, therefore, put the here the values. Therefore, efficiency is equal to 1 minus heat rejected. Heat rejected is mCv T5 minus T1. Therefore, mCv T5 minus T1 is the heat rejected divided by heat supply. Now, my dear students, here heat is supplied at two processes, that is heat supply at constant volume as well as heat supply at constant pressure. Therefore, total heat supply is equal to heat supply at constant volume plus heat supply at constant pressure. So, here the heat supply is mCv T3 minus T2, which is heat supply at constant volume, plus mCp T4 minus T3, which is heat supply at constant pressure. So, from numerator and denominator, m will take common and will get cancelled. So, mass will get cancelled. And my dear students, we know that Cp divided by Cv is equal to gamma. So, divide this numerator as well as denominator with Cv. Therefore, the equation becomes efficiency of dual cycle is equal to 1 minus, if I divide Cv here, T5 minus T1 divided by, if I divide here Cv, then T3 minus T2 plus, if I divide this Cp with Cv, then it is gamma T4 minus T3. This will be your efficiency of dual cycle, very much important parameter. In exam directly they can ask you this formula also, right? And my dear students, we have to check the other formula in terms of compression ratio, expansion ratio, cutoff ratio and pressure ratio or explosion ratio. So let us replace all the temperatures in the form of T1. So here T5 in the form of T1, T4 in the form of T1, T3 in the form of T1 and T2 in the form of T1. Put all these temperatures in the form of T1. So the simplified version becomes, therefore this efficiency thermal of dual cycle is equal to 1 minus, here T5 is T1 Rp Rc raised to gamma. Therefore T1 Rp Rc raised to gamma minus T1 whole divided by, now T3 is nothing but T1 Rk raised to gamma minus 1 into Rp, T1 Rk raised to gamma minus 1 into Rp minus T2. T2 is T1 Rk raised to gamma minus 1 plus gamma. T4 is, here T4 is written, T1 Rk raised to gamma minus 1 Rp T1 Rk raised to gamma minus 1 into Rp into Rc minus, here T3 is nothing but T1 Rk raised to gamma minus 1 into Rp, right? This is the equation. So my dear students, from numerator as well as denominator, if I take T1 common, in each and every term there is a T1. If I take T1 common, then T1 will get cancelled from numerator as well as denominator. Therefore, this T1 will get cancelled from everywhere. And from denominator, if I take Rk raised to gamma minus 1 common, see, in every term there is a Rk raised to gamma minus 1 in denominator. Rk raised to gamma minus 1, Rk raised to gamma minus 1, Rk raised to gamma minus 1. Therefore, the equation becomes 1 minus 1 upon Rk raised to gamma minus 1 from the denominator into, in numerator you will find that it is Rp Rc raised to gamma minus 1 divided by, in denominator you will find that, let us find the denominator for this equation, right? Here Rk raised to gamma minus 1 already taken common, therefore it is Rp minus 1, here Rp minus 1 plus gamma. Now from here, if I consider Rp common, then in bracket Rc minus 1, gamma Rp in bracket Rc minus 1. This will be your denominator. And this is your efficiency formula. Therefore, in terms of compression ratio, explosion ratio and cutoff ratio, the efficiency of dual cycle is equal to 1 minus 1 upon Rk raised to gamma minus 1 into Rp Rc raised to gamma minus 1 divided by Rp minus 1 into plus gamma Rp Rc minus 1. This is the formula for dual cycle. Now in this cycle, if cutoff ratio becomes equal to 1, let us say the first condition is cutoff ratio is equal to 1. That means which is nothing but V4 divided by V3. Therefore, V4 becomes equal to V3. That means the 3 location and 4 location at same point. Therefore, the cycle will become like this. See here on PV diagram, the cycle becomes like 1 to 2 reversible adiabatic compression, 2 to 3 constant volume heat supply, and 3 to 4 and 4 and 5 are at same location. 3 to 5 reversible adiabatic expansion, 5 to 1 constant volume heat rejection, and this is Otto cycle. This is Otto cycle. And let us put the formula in this efficiency of dual cycle. Therefore, efficiency of this dual cycle, if RC is equal to 1, becomes equal to efficiency of Otto cycle, which is nothing but, check here in this formula, RC is equal to 1. Therefore, here in numerator RP minus 1, and in denominator this term is 0, it is Rp minus 1. Therefore, Rp minus 1 divided by Rp minus 1 is 1. Therefore, the formula becomes 1 minus 1 upon Rk raised to gamma minus 1, which is nothing but the formula for efficiency of Otto cycle. And here you have formula. Let us put Rc is equal to 1 in this formula, and let us check. You will find this simplified version, which is nothing but efficiency of Otto cycle formula, right? And whenever Rc is 1, it becomes Otto cycle. Now, second is if Rp is equal to 1, that is explosion ratio, that is P3 divided by P2 becomes 1. That means P3 is equal to P2. Therefore, 2 and 3 are at same location. That means heat addition is at constant pressure only. Now, if I draw PV diagram, here pressure versus volume diagram, and 2 and 3 are at same location. Therefore, 1 to 2 reversible adiabatic compression, 1 to 2 reversible adiabatic compression, and 2 and 3 are same location. 3 to 4 constant pressure heat supply, 4 to 1 reversible adiabatic expansion, 4 to 5 reversible adiabatic expansion, 5 to 1 is constant volume heat rejection. This will be your cycle, and this is a dual cycle, that is reversible adiabatic compression, constant pressure heat supply, reversible adiabatic expansion, and constant volume heat rejection. This is a dual cycle, and which is nothing but diesel cycle. This is a diesel cycle or not, right? Therefore, dual becomes equal to diesel cycle. Therefore, the efficiency of dual cycle, if Rp is equal to 1, becomes equal to efficiency of diesel cycle, which is nothing but, put here Rp is equal to 1, then simplified version you will find as this efficiency is equal to 1 minus 1 upon Rk raised to gamma minus 1 into Rc raised to gamma minus 1 divided by gamma Rc minus 1. And here you have formula. In this formula only you have to put Rp is equal to 1, and you will find this result, and this is the result of efficiency of diesel cycle. And therefore, dual cycle efficiency becomes equal to diesel cycle efficiency if explosion ratio becomes equal to 1, and this dual cycle efficiency becomes equal to Otto cycle efficiency if cutoff ratio becomes equal to 1. Now, in case of dual cycle, the heat addition order, that is heat supply order, is heat is added at constant volume first, and then heat is added at constant pressure later. Hence, during heat addition, constant volume is first, and then there will be a constant pressure process. So, the heat addition order, heat supply is equal to heat supply at constant volume plus later heat supply at constant pressure. And my dear students, area enclosed by the cycle is network. Therefore, area enclosed by this PV cycle is network. Right, this is a network for the given order. Let us assume that the heat gets added at constant pressure first and then at constant volume. Therefore, from this location 2, heat gets, if I assume heat gets added at constant pressure first, therefore 2 to 3 will be here, and then at constant volume, then 3 to 4 will be like this, right? So, during this heat addition order, if I follow this heat addition order, see here, this area here, this area is a loss of work, right? That means area enclosed by the cycle is decreased by this blue color shaded area. Hence, net work is reducing. Therefore, this theoretically, this is not feasible to add heat at constant pressure first and later at constant volume. Theoretically, it is always to add heat at constant volume first and constant pressure later for obtaining maximum work output, because this order 1 to 2, 2 to 3, 4 and 5, this order gives maximum area in the cycle. And my dear students, practically also this is impossible to add heat at constant pressure first, because during constant pressure heat supply the piston is moving, and during constant volume heat supply the piston is stationary. So At TDC, at constant volume, heat is added, and from 3 to 4 and 4 to 5, piston is moving, right? But if heat addition order is changed, that is, if heat is added at constant pressure first, therefore from TDC to this 3 point, piston will be in motion, right? And 3 to 4, the piston will stop, that is here at this location, the piston will stop for some time to get heat added at constant volume, and during motion it is practically impossible to stop the piston for constant volume heat supply process. Therefore heat addition order is always at constant volume first, later at constant pressure. Thank you dear students. In next lecture we are going to understand Linear cycle of heat engine.